So previously we've seen the reposition strategy. We're going to now look at the nature of deterministic online algorithms for the K Canadian Traveler problem. So there is no deterministic. There is no deterministic online algorithm that has competitive ratio less than 2k plus 1. Remember, k is the number of traps at most. So we know that, right? So we're going to be establishing this lower bound result. And I must stress that it says that there is no deterministic online algorithm that has property like where we can get that competitive ratio less than what we had in the reposition strategy. So you're going to find that the intuition that we had before is going to be rather helpful for how this is going to work. Okay? And remember, the claim is about any deterministic online algorithm, right? It's any one. It's not just the reposition strategy. It could be any other deterministic strategy. So our proof has to apply no matter what the strategy is, what the algorithm is, what the policy is. So here we go. So you're going to see right away that I'm not going to make any assumptions about what the algorithm is other than it's deterministic, okay? That means that there's no coin flips, no randomization. That means that when I execute it once, it'll give me the same outcome, as opposed to if, say we're talking about randomized online algorithms, that's where you have coin flips, and the behavior of the algorithm can change due to those results of those experiments, those randomized experiments, like the coin flips. So we're going to consider. So the game plan is as follows. I'm going to consider any deterministic online algorithm. And I'm going to do is I'm going to construct an instance that uses information about what that algorithm does. This is going to be something that's called an adversarial argument. So consider any deterministic online algorithm A. And for any epsilon greater than 0, and for any epsilon greater than 0. So I'm going to introduce this epsilon term. This is going to help me when I build the instance. If you don't like that, you can introduce it with another constant and rescale everything appropriately. I'll let you think about that if this is an issue for you. For A, construct an instance with weighted graph G is equal to VE as follows. So here's what I'm going to do. I'm going to draw a picture. If you want the actual explanation, it will be in the notes because I just want to save you some time. So I'm going to construct this graph, and it's going to look like this. So I'm going to have S and T. And then I'm going to introduce exactly K plus 1 disjoint paths. The only thing in common are S and T. So it's going to have a path that goes from S to V1 for the first path. Its weight of the first edge is going to be 1. The second edge is going to be epsilon. Then I'm going to have a second path, V2. It goes to T, weight 1, second edge, weight epsilon. And we're going to keep doing this. So you're going to have a whole bunch more, potentially, depending on what K is. And then we're eventually going to have it where you get VK for the kth path. Again, weight 1, second edge weight epsilon. And the last one is going to be VK plus 1. with weights 1 and epsilon, like this. Now, I haven't told you where the traps are, okay? So what I'm going to do is I'm going to make a little interesting observation here. Notice that when I give you this graph, finding a path from S to T, notice you could just simply go across one of these paths, right? Notice that if you actually think about it, I'll try to let you convince yourself of this, but here's the main observation. So if k of the k plus 1 paths have traps, for A, to find a path should the first k be trap edges, oh, sorry, have trap edges, have trap edges, have trap edges, because remember, if I have k of the k plus 1 have trap edges, like if I put the trap edges on edges like these, so if I pick them carefully enough, what I can do is I can force the algorithm to keep going like this, right? Until it gets the last one, just like what we had intuitively. It should remind you a little bit of the reposition strategy, right? However, this is for any deterministic online algorithm. So we can't just simply say, oh, just label those, because the algorithm might pick a different path than what you're thinking. So if k of the k plus 1 paths have traps, for A, to find a path from S to T, this can corresponds to some permutation of the k plus 1 paths. So the permutation tells you the order the paths are examined. So now if you have this set up, notice it's just going to be a listing of the paths in the order for which every time it runs into a trap for the first k, and then the last one's a successful one. So here's how I'm going to set this up. So let path pj be the final path, of all paths. So keep in mind, I'm talking about this as P1, P2, P3, P4, P5, all the way to PK, PK plus 1. But remember, it may not be in that order. So I'm going to just give them the names of the paths that they get examined by A, the algorithm. Of all paths, P1, P2, all the way up to PK plus 1, selected by A. So notice this depends on the algorithm. So P1, P2, all the way up to PK plus 1, these are going to be the paths that get selected. For each path pi with I is not equal to j, remember pj is the last one, set a trap on the edge vi t. So as a result of this, you get how many edges? How many traps? K. You get K traps. So you're going to set traps, like for example, if the algorithm examined all of them in the order from 1 to K plus 1, which it doesn't have to, just to be very clear. What will happen is it'll set a trap here, set a trap here, set a trap here, and so on and so on. And then it'll leave this one open so you can get to T. Again, the whole idea is that you're trying to build an instance that causes it to perform at least a certain amount of work. So we're not really caring about time complexity here, which many of the lower bound results that you may think of for adversaries might be the case. But for online algorithms, it's very often the case that you want to try to make the solution's value as nasty as you possibly can, at least. So there's K traps. And on top of that, there exists a way to get from S to T. So notice here, so now let's put this all together now. So regardless, observe that the ST path selected by A has length, so it has the following length. So remember, like I said, it's going to go there, back, there, back, there, back, there, back. Sorry, I feel like I'm doing a dance. There, back. It's going to go there, back, all the way until it gets to the last one, prescribed by the algorithm A. But what are the there, back? They're all edge weights of 1, right? So we're going to have 2 times 1, so for there and back. It fails for the first K, so this is where you get a... So it failed to find T in these cases. And then it has that the last path. If you simplify this, you end up with 2K plus 1 plus epsilon. But what's the length of the shortest ST path if you knew where all the trap edges are? What would it be? You just use PJ, right? Remember, PJ is the one that is actually the one that will be successful. It's the last one. But the thing is, that's also the optimal offline solution, right? Well, that is one. The shortest ST path has length 1 plus epsilon by taking path PJ, right? And it's PJ only. It doesn't have any of this back and forth business. It just goes across PJ to go from S to T, right? That's all it's going to do. Nothing else going on. There's nothing else to see here. So now let's put this all together. Therefore, the resulting ratio for A's competitivity, cannot be less than the following. Because remember, this ratio is regardless of what A does. Remember, that's the whole trick here, is that this argument works regardless of what the algorithm does. So remember, we built an instance that will cause the algorithm to do is, we try to lead it as long as possible, okay? Cannot be less than. So remember, this is the value of the solution that we get. The length of that path is 2K plus 1 plus epsilon, all over the optimal, which is 1 plus epsilon. Which proves the claim. as epsilon is greater than 0. So if you're wondering why this is the case, if you're not seeing it right away, actually I should make sure I indicate the end of the proof. If you're not seeing this last point right away, just note that this ratio is less than 2k plus 1. That's the first thing. The other thing is that if you take epsilon, so if you're looking at this really quickly and you're not sure, just take epsilon and approach 0. You'll notice that this goes to 2k plus 1. So it's less than 2k plus 1. And also, if you take epsilon and approach 0 with it, for this ratio, it's 2k plus 1. So this proof actually tells you that for any deterministic strategy for the K Canadian traveler problem, aka escaping our haunted house, it cannot have a competitive ratio less than 2k plus 1. And we already established that the reposition strategy matches 2k plus 1. Very fascinating stuff, right?